Hello, students. I welcome you to your favorite YouTube channel, Physics for Everybody. Today, we'll be taking the May June 2024 paper 6 variant 1. Okay, that's the alternative to Physics Practical, Physics 0625. Without delay, let's go straight to the first question. Question number 1. A student investigates the stretching of a spring. Now, we have this apparatus. Let's go straight to the question. The student measures and records in table 1.1 the unstretched length L naught of the spring. He does not include the loops of the ends of the spring in the measurement. The value L naught is the length of the spring when the load L of the spring is 0.00 Newton. Describe one technique you would use to obtain an accurate value of L naught. Draw a diagram to illustrate your answer. So in order to get accurate reading of length here, you don't just have a spring here and a meter rule and then use your eyes to try to visualize what parts of the meter rule that the spring is on. So what you do is that you have a set square which will slide along the length of your meter rule. Okay, you slide the set square upwards, okay, and you don't include this part of the spring because those are the parts of the spring that do not obey Hooke's law. Okay, so only this part of the spring will be included in measurements of length. So what you just do, you just draw a diagram, include a set square to indicate that you're using it to take measurements of length, and that is what we have here. Yeah, so this is the diagram you draw. Okay, this is the diagram you will draw, and this is the explanation you will give. By sliding a set square along the length of the meter rule in order to avoid parallax error. So this is a technique used to avoid parallax error. Okay, let's go straight to the next part of the question. The student suspends a load L equals to 1.00 Newton from the spring. He records the new length L of the spring in table 1.1. He calculates the extension E of the spring using the equation E equals to L minus L0 or L naught and records the value of E in table 1.1. The student repeats the procedure using loads L equals to 2 Newton, 3 Newton, 4 Newton, and 5 Newton. The readings and the results are recorded in table 1.1. Calculate the extension E of the spring using the equation E equals to L minus L0, where L equals to 5 Newton. Record this value in table. Record this value of E in the table. So we have to get the extension when the load is 5 Newton. What is the original length of the spring? We have the original length L0 of the spring as what? Let's see. L0. We are looking for the original length of the spring. Okay, the original length of the spring will be the length of the spring when the load equals to 0 Newton. Okay, when the load is 0 Newton, that will be the length. Okay, so since this L is 2.1 centimeters, that will be the L naught. Okay, so L naught is the length of the spring when the load attached is 0 Newton. So that's what we're using to calculate the extension E. E equals to L minus L0. The length when the load is 5 Newton, the length is 23.7 cm. So we have 23.7 minus 2.1, that will give you 21.6 centimeters. So that's the length we have, 21.6 centimeters. Now the next thing we are doing is to plot a graph. Plot a graph of L on the n-axis, okay, sorry, load in Newton, okay, on the y-axis against E, which is extension in centimeter, on the x-axis. Start both axes at the origin 0, 0. Draw the best fit line. Okay, so the first thing you do is you draw the axis. We have the L axis. So we have the L axis, load in Newton, which is being placed on the y-axis. And then we have the E axis or extension in centimeter. Okay, so what are the values of load? We have 0, 1, 2, 3, 4, 5. So you can do 0, 1, 2, 3, 4, 5. You make sure you use straight ruler while doing this on your answer sheet. What are the values of extension? Okay, since we have E on the x-axis, the value of E ranges from 0 to 21.6 centimeters. So what you can do, you can have 5, 10, 15, 20, 5, 10, 15, 20. You can also choose to make your scale bigger by putting 4, 8, 16, sorry, 4, 8, 12, 16, 20. Either of these scales would work, okay? Yes, they'll cover the range of value, which is 21.6 centimeters. So either of these will work, okay? 24, yeah, this will be 24. See, either of these scales would work. So I've done this here, okay? So to make your work easier, I'll just show this here. I've already plotted the points, okay? So I use 1, 2, 3, 4, 5, and I use 5, 10, 15, 20, 25 for the values of E. Okay, so let's see the points I plotted. When the load is 0 Newton, extension was 0 Newton. So I went to load 0 extension 0, which is the origin, and I put a point there. Okay, that's this X you have here. The second point I have is let me just pick the point from here. The second point I have is when the load is 1 Newton, extension is 3.9 centimeters. When load is 1 Newton, extension is 3.9 centimeters. So I came here. Don't forget that this is the load axis, load in Newton. So when the load is 1 Newton, the extension is 3.9. So I came here. If this is 5 and there are 10 divisions here, um, you know, this big box here is on the x-axis, we have 5 here. So if I divide 5 by the number of smaller divisions, which is number of smaller boxes, I will have 0.5 centimeters. So each of these boxes here represents 0.1 centimeters, 0.5, 0.5 centimeters. That simply means what I have is 0.1, 0.5, 1.0, 1.5, 2.0, 2.5, 3.0, 3.5, 4.0, 3.9 centimeters can be approximated as 4. That's why I traced from 3.9 centimeters, and that's where I placed this point. Don't forget that that point was taken from 3.9 centimeters on the extension axis and 1 centimeters on the load axis. That's why on my graph, I picked 3.9 centimeters, which is approximately 4 here, and I picked 1 centimeter. That's why I put this point. So I do likewise for the other point. I'll go to a load of 2 Newton, and I'll pick my extension as 8.5 centimeters. So back to the graph. When the load is 2 Newton, extension 8.5, let's see if this is 5, 5.56, 6.57, 7.58, 8.5 will be here in the middle here. So this 8.5. So I just traced 2 Newton to 8.5 centimeters. That's why I put this dot here. So you do likewise for every other point, okay? Pick the value of the load, pick the value of the extension. That's how I do every other one. Let me just show you the third one quickly. So the third one, I picked the load of 3 Newton and an extension of 12.8 centimeters. So 3 Newton, extension of 12.8, 10, 11, 12, 13, 12.8 is so close to 13. That's why I picked my point. I placed my point here. Let me see if I even did that correctly. So I place the point here. Yeah, that's it. So you have to be very, very careful when placing your points, okay, to ensure you don't make any mistake. So that's how I got every other point, okay. And then the next question asks us to Let's proceed to the next question. So plot the graph and draw the best fit line. Okay, line of best fit. So line of best fit is a single line that passes through all the points I've plotted. So if I had plotted my point, let's assume I plotted my points like this. So I'll just draw a straight line that passes through this point. And if it does not pass through all the points, if any point is being left out, then those 2 points that were left out must not be on the safe side, on the same side. Look at this now. The 2 points that are left out, they are at the top. This is a very wrong line of best fit. Okay? So let us do another one. What if the points that are left out are on the same side, like this? This is also a wrong line of best fit. And if the points I've plotted not picking on the slope, if I had 2 points up here, then the other two are on the other side down here, this is also a wrong line of best fit because I could have drawn a better one like this. Yeah, I could have drawn a better line of best fit like this. So if you have some points outside the line, those points must not be on on, like, it shouldn't form an X. Like those that are being left outside, being top left, bottom right, that is wrong. Okay, they should be evenly distributed. What I mean is that if I'm having 1 point here, one here, then another two here, well, that's acceptable. But the points that are falling outside should not form at the two extreme sides. That means all of them top left, the other ones bottom right. That is wrong. Okay. Yeah. Okay. Don't forget that this line is what I'm using as my frame of reference. So if I say top left, I mean top left of this line. Okay. I'm using this line as my origin now. Okay. And this is the bottom right of the line of best fit. So let's see what I drew as the correct line of best fit for this graph. So this line I drew here, the points that fall within the line, I have this is on the line, this is on the line, this one is on the right hand side, this is on the line, this is on the line. So only one point is falling out, and that point is falling on the right hand side of the line. So that is still acceptable. Let's proceed to the next part of the question. Determine the gradient G of the graph. Show all your working and indicate on the graph the values you use. So how do I determine the gradient? The gradient is the y, the x. So change in value on the y-axis divided by change in value on the x-axis. How do I determine my dy dx? The first thing I do is I'll draw a big right angle triangle. Okay, I'll draw a big right angle triangle along the slope. So my big right angle triangle could be as big as this, okay? And then I'll pick values at the two extreme, be it top here as my x2, y2, and then I pick values down here as my x1, y1. This I've done here. Okay, so I'll just use what I've done here to make it faster to save time. So I've done it here. I've drawn my line of best fit and I've picked my value, okay? So my values are L2, E2, okay, because it's a graph of L against E. So L2 is the value I have here, which is 5 Newton. Then L1 is the value I have here, which is 1 Newton. What about E2? E2 is from this point, I'll trace it downward, the value I have here, which is like 21.5 centimeters. Then E1 is the value I have from this point, trace it downward here, which is 4 centimeters. So I drew my big right angle triangle, okay? Then from this point here on the big right angle triangle, I trace it here, I have 5 centimeters. So I've listed these values here, L2, which is the value of L on the L axis, the higher one, then L1 from here to the L axis, I have 1 Newton as my L1, and my E2 is 21.5. That means from this point, trace it downward, you have 21.5 here. Then from this point, if you trace it downward, you have 4. So that's why my E1 is 4. So gradients can be gotten by using dy dx, change in y divided by change in x. Yes, okay, let me just go back to when I did here. So that will be L2 minus L1 divided by E2 minus E1. My L2 is 5 Newton, my L1 is 1 Newton, and then my E2 is 21.5 centimeters. My E1 is I think I got 4 centimeters as my E1. Let me check it. Yeah, my E1 is 4 centimeters. The value here is 4 centimeters. As you can see from the graph here, the value is 4 centimeters. So if you do this and divide, this should be 5 minus 1 is 4. 4 divided by 21 minus 4, that will be 17.5. 4 divided by 17.5 should give us 0.230. And that's how I got this answer here. Okay, so I got my value as 0.230 Newton per centimeter. Now, G is numerically equal to the spring constant. Record the value of K to a suitable number of significant figures for this experiment. Include the unit. So this value I got here, the unit was not necessary, but stating it here is very important and include the unit. And I've written it to two significant figure. So that's it. Once you do that, you get all your marks for the question. Question number 2. A student investigate the resistance of a wire. In figure 2.1, the circuit, figure 2.1 shows the circuit used. Now this is the circuit. This is a sliding contact, okay, which can be represented with a jockey, okay, or you may choose to use a crocodile clip. This is a resistance wire. This is an ammeter, voltmeter to measure voltage across the wire. This is a DC power source. This is a switch. The student measures the current I in the circuit. She places the sliding contact S at a distance D is equal to 50 centimeters from B. So starting with a distance of 50 centimeters, she measures the potential difference V, that's V50, across length D of the resistance wire. When the student places the sliding contact here, the voltage across this from here to this sliding contact, he called it V50. That means voltage at a distance of 50 centimeters. Figure 2.1 shows the ammeter and voltmeter. Record the readings on the ammeter and voltmeter. Okay, what do we have on this ammeter? Let's see. If this is 0.2 amperes and there are 10 divisions, then each small division will represent 0.2 divided by 10. 0.2 divided by 10 will give us 0.02. So each of these smaller division will be 0.02 units. So it's 0.2, 0.22, 0.24, 0.26, 0.28, 0.28, 0.3. This should be 0.3. This should be 0.32, 0.34, 0.36. Ammeter is showing us 0.36 amps. And the voltmeter is showing us if this is 1 and there are 5 divisions, then I have 1 divided by 5, which is 0.2. That simply means each of the smaller division here, the smallest division here is 0.2 volts. So if this is 1, this is 1.2, then this one will be 1.4 volts. 1.4 volts. That's what I have. So my ammeter is showing 0.36 amperes and my voltmeter is showing 1.4 volts. And if you want to write both to the same number of decimal figure as 0.140 volts. But it's fine. It's okay to write to 2 significant figure, which is 1.4 volts. Current written to 2 significant figure, voltage written to 2 significant figure. Oh, I've done this already, but it's fine. Calculate the resistance R50 or 50 cm of the resistance wire using the equation R equals to V over I. Since R equals V over I, voltage is 1.4, current is 0.36, divide 1.4 by 0.36, you get 3.89. And if you want to write it to 2 significant figure, it will be 3.9 ohms. That's if you want to write to 2 significant figure. Now you also to calculate R1, a value for the resistance per centimeter of the resistance wire using the equation. And you want to get resistance per centimeter, just divide the resistance by the length. And the length we used in the first case is 50 centimeters. So divide the resistance by the length, you get 0.078 ohms. That's it. Now the student repeats the procedure in A using D equals to 75 cm and calculates R2 using the equation R2 equals to R75 over D. This student is repeating the experiment and is using a distance of 75 centimeters. So the student repeating the experiment is using a distance of 75 cm. That's why the experiment is being repeated. Okay, so let's see what the student does while repeating the experiment. Now, this student then proceed to calculate R2 using the equation R2 equals to R75 over D. So the resistance at 75 centimeters, he got his resistance at 6.1 ohms. He got the voltage as 2.2. Then he calculated R2. Of course, if you divide R75 by D, which is 75, divide 6.1 by 75, you get 0.0081. Okay? Yeah, resistance per meter, or per centimeter rather. It's fine. This unit is not necessary. You don't have to state it. Let's proceed. A student suggests that the resistance per cm of the resistance wire is constant. State whether your results support this suggestion and justify your statement by reference to the results. So, what the student says, is it correct or wrong? Now, let's compare. The value of R2 is 0.081, but our own value of R1 is 0.078. Do you consider these two values to be close to being equal within the limits of experimental error? There is a hint though. What is that hint? What we do is that if the gap rather, or the deviation, if the difference between these two numbers is less than 5%, okay, is less than 5% of the biggest number, then you can say fine, these two numbers can be considered equal within the limits of experimental error. But if the difference between these two is is bigger than 20% of the bigger number, then you say the difference is too much to be considered being equal within the limits of experimental error. Fine, during the experiment there can be errors, so you are not expected to get equal values for the two values. But the two values, when they are close enough, you can consider them equal. So this is the hint, okay? So when you divide the difference between the two values by okay, divide the difference between the two values by what? By the highest value and multiply your result by 100%. When you divide the difference between the two values by the no, we're using the smallest value. Yeah. So when you divide the difference between the two values by the smaller value, and then you multiply your answer by 100, okay, if what you are getting is smaller than 5%, then the two values are equal. But if the two numbers, if your result is less than 5%, then those two figures are close enough to be considered equal within the limits of experimental error. But if your result is greater than 20%, then those two numbers cannot be considered equal within the limits of experimental error. But if you get any value within 5 to 20, then it is left to your own justification, okay? Some consider values less than 10 to be equal within the limits of experimental error, and values higher than 10 to be outside the limits of experimental error, okay? But as for 5%, everybody considers it equal, and anything beyond 20 is outside. Anything within the range is subject to your own judgment, as long as your explanation rhymes with what you get. Let's get that though. What we got is 0.078. Okay, let's subtract 0.078 from 0.081. What we get is 0.003. Now let's see. Divide 0.003 by the smaller value, which is 0.078, and multiply by 100. If what you are getting is smaller than 100 is smaller than 5%, then you can say it is equal. And if it's bigger than 5%, but less than 20% is left to your judgment. But anything bigger than 20%, they are not considered equal. Let's see 0.003 multiplied by 100%, and then I'll divide this by 0.0078. Let's see if I get anything within around that 5%. 0.003, I'll do that again. Oh, divided by 0.078. Yeah, this is what I'm supposed to do. 0.003 times 100% divided by 0.078. I got 3.84%. 3.8%. So 3.8% is small enough. Okay. So since what I got is 3.8%, that means the deviation between these two values, is just 3%, 3.8% deviation. Or if you want to write it to the nearest whole number, 4% deviation. That can be considered equal. Okay, so those two numbers can be considered equal within the limits of experimental errors. Okay, yeah, that's it. That's how you work with this. And if you want to learn more on this, you go and learn about uncertainty under the AS and A level physics. That's how you get to understand more about these concepts. So I've stated my answer here. The difference between R1 and R2 is very small and within the limits of experimental error. The student plans to plot a graph of resistance R against length D to test the suggestion. Suggest suitable additional values of length D to use. If you are performing an experiment and you want to plot a graph, we want you to have about 5 values. Yeah, so experiments that involve graph, you need about 5 values. So we already have 2 values. Okay, the one we did for R1, then the one the student did for R2. So just put 3 other values, and if you choose to put 2 other additional values, it's fine. Just don't go beyond 100 centimeter because your resistance wire is usually up to 100 centimeters or 1 meter. Okay, and of course, you know very well you can't pick any value below 0. In fact, 0 even shows that no length has been picked. So pick values bigger than 0. You can pick 10, 20, 30, 40. Okay, yeah. 50 and 75 has already been done for you. So that's fine. That's how you pick your values here. Make sure you have 5 values. The last question is a variable resistor is a circuit symbol that can be made using a coil of resistance wire. Draw the electrical symbol of a variable resistor. That's what we have here, okay? Just the symbol of a normal resistor with an arrow across it, indicating that you can increase or reduce the resistance. Now we move to question number 3. A student investigates the image produced by a lens. Figure 3.1 shows the setup. So we have an illuminated object, we have a lens, we have a screen. So what's next? Figure 3.2 shows the height h naught, okay, or h0 of the illuminated object. This represents the illuminated object. When you're performing experiments on optics, okay, which I will show with this simulation. So you have an illuminated object, okay, which represents something that gives out lights, okay, and then you have the image being formed here. And if I want to show it with a luminous object, okay, so this is the luminous object bringing out rays of light. This is my screen here. So you can position the illuminated object at any point and images will be formed. All you have to do is to move your screen until a sharp image is formed, okay. So here you can see where the rays cross each other. Yeah, so where those rays cross each other, that represents the position of the image. So that's one thing about this. And yeah, so you continue to move the screen until you have a sharp image. Keep your eyes on the image that is formed. Okay, you continue to move your screen back and forth until a sharp image is formed. So on this simulation platform, when you have nothing at all on the screen, that's when you consider a sharp image to have been formed. So here, a sharp image is considered to have been formed here. Let me check it by bringing back the rays of light. Yeah, so where these rays converge. That's where the image is formed. So let's get back to this. So on figure 3.1, measure the distance x. On this figure, how you measure this distance? Place a meter rule here, okay? Place a meter rule here and use the meter rule to measure this distance x. That's all. And when I did that, I got 1.6 centimeters. Okay, the first thing I did was to measure h0. I placed my meter rule here. I measured h0 to be 1.6 centimeters. And then I placed my meter rule up here to measure x, and I got 2 centimeters as my x. Okay, back to what we're talking about. Calculate the scale ratio R using the equation R equals to U over X. And you are giving U as 20 centimeters. Okay, since U is 20 centimeters, divide 20 centimeters by 2.0. I will get 10, and that's how I got this R as 10. The next question says, the student moves the screen until a focused image is formed on the screen. On figure 3.1, measure the distance Y. So when I place my meter rule here, in order to measure the distance Y, the distance between Y and the screen, when I place my meter rule here and I measured this distance, I got 6.2 centimeters, and that's what I have here. Now, this is the main question. This is where you start working. Calculate the actual distance V between the lens and the screen using the equation V equals to RY. You know, we have already gotten the scale factor. We've gotten the scale factor R as 10. So if you multiply the scale factor by the distance you have on the diagram, which is 6.2, then we get the actual distance as 62 centimeters. So that means if you are performing this experiment in the laboratory, if the object is at a distance of 20 centimeters from the lens, then the image will be at a distance of 62 centimeters, okay? That means I have to move this image backwards more, okay? So if the distance is 20 centimeters, this distance here will be 62 centimeters before a sharp image can be formed. I believe that's clearly understood. So the next question we are to answer is to calculate the focal length f of the lens using the equation. Now this is the formula we use to calculate focal length, uv divided by u plus v. What is our u? We were given our u as 20 centimeters, okay? You were told that the object was placed as 20 centimeters. Yes, and we calculated our v as 62 centimeters. So just substitute those values. 20 times 62 divided by 20 plus 62. 20 times 62 gives us 1240. 20 plus 62 gives us 82. 1240 divided by 82, you get 15 point. You get 15 point. When you just approximate that, 1240 divided by 82, you get 15.12. Write it to two signal figure, you have 50 centimeters. 15 centimeters is the focal length. Now, in this type of experiment, it can be difficult to judge the screen position that produces the clearest image. State two precautions or techniques to overcome this difficulty. You are told that it can be difficult to judge the screen position that produces the sharpest image. We're able to see these lines because this is a simulation, but in a real life setting, these lines will not be here. You know where these lines cross now. This is the position where you have the sharpest image. If I bring my screen here, the sharpest image will be formed here. That's a real life setting. But if you don't have these rays here, if I click on none, so that these rays will not be shown, how do you get the position of the image? This is what you do. You know, you have the screen, you have blurred image, okay? It's not sharp. And if you bring it too close, you see I have blurred image. So what you do is you'll be moving your screen backwards, you move it forward a bit, you move it backwards a bit until what I said that so this is where the image will be formed. So in a real life setting, in the laboratory setting, is at this kind of position that you have a very tiny image and sharp image on the screen. So when you perform this experiment in laboratory, this will be the position where the sharp image will be formed. Then you can measure this distance from here to the screen to get the image distance. So if I click on principal, you see that the rays of light will converge here, okay? Any other point, you have blurred image, but where they converge, that's where you have sharp image, which can be seen as nothing being formed on the screen, only for the simulation. But in the real life setting, you have a sharp image on the screen. So the precaution, you move the screen backwards and forward until a sharp image is formed on the screen. Then the second one, you perform the experiment in a dark room or a poorly illuminated laboratory. So that is how you see sharp images. If the room is very bright, then when rays of light converge on the screen, it won't form a sharp, like the image will not be clearly seen because of interference from the rays of light in the room. Okay, the next question, figure 3.2 shows the sharp image. Let me remove this. So figure 3.2 shows the shape of the illuminated object. The image of the object is enlarged. Draw the diagram to show the image you would see on the screen. Okay, so figure 3.2 shows the illuminated object. Let us see the object again. This is the object. So if this is the object, then the image will be inverted. That means it will be upside down. Okay, so just draw an inverted triangle. And that can be visualized when we have a shape, any shape of object here. Let me click on marginal again so you can see where the image is formed. You can see the object, the image formed is inverted, whichever shape of object you use. Okay, if you use an arrow, the image form will be an inverted arrow. Use a penguin, the image form will be an inverted penguin. So that's the general characteristics of the image formed by a converging lens. Okay, when a real image is formed, real images are inverted. Okay, yeah, since the image is captured on the screen, then it's a real image and it is inverted. The fourth question, the first question is always on planning. Let's go. Okay. The students investigate the bending of composite strips of wood when they are loaded at one end. The composite strips are made from identical layers of wood stuck together as shown in figure 4.1. Plan an experiment to investigate how much composite strips bend when they are loaded. How much? You want to investigate to what extent they bend when they are loaded at one end. Figure 4.2 shows the setup the student uses. The student has a number of composite strips made with two or more layers of wood. So since there are different composite strips that are made with two or more layers of wood, so you can have a composite strip having just two layers of wood. You can have a composite strip having three layers of wood. You can have another composite strip having four layers of wood. I want to investigate how it bends when loaded. What will you do? Now, these are things you can do. You can plan the experiment in terms of number of layers that are stuck together. So you can have two layers of wood and then you attach a load. So when you attach a load here, what happens? It bends. Then you go to the one with three layers of wood, apply a load again. Which one would bend more? The one with two layers of wood will bend more. Why? Because it's not as strong as the one with three layers of wood. So you can plan these experiments in terms of number of layers of wood, increasing the number of layers of wood and increasing the load. You can also plan the experiment in terms of the weight of load. Okay, so when you are performing these experiments, one value will be increasing. While one value is increasing, you are checking the effect it has on another value. Okay, that's how you perform physics experiments. Increase one value, okay, and see the effect of that value you're increasing on another value. But while you are doing this, there's a third variable or even third and fourth variable you keep constant. So now you can do it in terms of weight or load, like you have different weights. One is 1 kilogram, the other one is 2 kilogram, okay? The other one is 2 kilogram, and then you have another load, 3 kilogram. So you can be increasing the weight of the load you are adding. Okay. So as you increase the weight of load, check to what extent it bends. Okay. So if you are doing this experiment in terms of increasing the weight of the load you are adding, then the number of strips of wood must be kept constant. So you must use only strip of wood that has a given number of you must use composite wood that has a given number of strips. Okay, if you are using the one that has 3 strips of wood, that is what you use throughout the experiment. Use the one with 3 strips. So continue to increase the load. You can start with a load of 1 kilogram. Okay, load it. The wood bends. Check to what extent is bent. How do you get to what extent is bent? This distance gives you the extent of bend. Remove that 1 kilogram load, put another load of 2 kilogram. Okay, put the 2 kilogram load, measure to what extent it bends. Okay, remove the 2 kilogram load, put a 3 kilogram load. Okay, check to what extent of bend. So that's what another thing you can do. Okay, the third way you can even perform the experiment is to use one fixed mass, probably the 1 kilogram, then you change the length of the wood. You can start with a strip of wood having a length of 50 centimeters. Okay, load that wood, put that wood here. Okay, measure the extent of bend, then remove that wood, put another wood of length probably 60 centimeters. Okay, put the load, check the extent of bend, remove that load, remove the wood, replace the wood with another one having length 70 centimeters. Continue to increase the length of wood and check the extent of bend. And if it is the length of wood you are increasing, then you must use one particular load. Okay, yes, if you are changing when you are changing one value, every other value will be kept constant. So the mass of the load must be 1 kilogram throughout, and the number of strips of wood must also be constant. If you are using if you are using a composite material that has only 2 strips of wood, it is that 2 strips of wood you would use throughout the experiment. You don't increase the number of strips of wood. So there are 3 ways to actually approach this experiment. Yeah, there are 3 different ways of approaching this experiment. Either by increasing the number of strips of wood, keeping every other value constant, or by increasing the mass you are placing on the wood, keeping every other value constant, or by increasing the length of the wood, keeping every other value constant. Now, this is what I've done. I've answered this question in both ways. Look at the first thing I did in this experiment here. Keep an eye on this. So this is what I have. Okay, the first thing, state the variables that you are testing. This is what I did. Attach a 50 cm long wooden strip to a clamp as shown in the diagram. Measure the initial length h1, initial height h1 of the unclamped end of the composite strip. So what I did is that I measured the initial height. That means from here to ground level. I placed my meter rule here, okay, and I measured this and called it my h1, the initial height. So after loading the wooden strip, I then measured the new height from here to here. Okay, I called it my h2, my height h2. From here to here, I called it h2. Now, if you take the difference, the bend now, extent of bend will be h1 minus h2. If you take that difference, you get the bend. Okay, h1 minus h2. So measure the height h1 of the unclimbed end of the composite strip from ground. Attach a load of mass m equals 1 kilogram to the unclamped end of the composite strip and measure the new height h2 from the ground. Now calculate the difference in height E equals to h1 minus h2. Repeat the procedure with other masses m equals to 2 kilogram, 3 kilogram, 4 kilogram on the unclamped end of the strip. So you add other masses to that, okay? Then keep the length of the composite strip and the number of layers of wood constant throughout the experiment. Record your readings and calculations on the table below. What table will I have? I'll have the length. Okay, I'll have what am I doing? I'm increasing what? I'm increasing the mass. So I'll have the mass. I'm representing the mass as m already. So I can have m in kilogram against what? Against the extension E in centimeters. That's all I need to tabulate, okay? And you may choose to have all your values on your table like H1, the original height, H2, the new height, okay, and then you now put E equals to H1 minus H2, okay. You may choose to put your table this way. Yeah, E equals to H1 minus H2 in centimeters. If you have chosen to write down all the values like this, fine. The last thing, plot a graph of M, okay, which is the mass, against the difference in height E, okay, of the composite strip from the ground. Then the last thing you do, calculate the slope of the graph. But now when you ask, after doing this, you now go and check if you have answered this question correctly. Did you state the variables that you are testing? Of course, I stated that I'm testing the extension, okay, the effect of mass, the as the mass increases, what's the extension? List any additional apparatus. Did I list that? No. So when performing practical experiments, after writing, you have to go back and check, okay, if you have actually answered the question correctly. Um, what did I say? Measure the initial height H1. Measure the initial height H1. If I want to include additional materials, I could have just said use a meter ruler to measure. So I could have stated it this way, okay? That I'm using a meter ruler. Oh, look at the way I wrote ruler. Use a meter ruler to measure the initial height. So here now, by doing this, I've indirectly measured the additional instrument I'm using. So once you do this, make sure you are very careful. Okay, I've explained briefly, I've stated my key variables to keep constant. Okay, I've stated the variables I keep constant during my experiment. Okay, I've drawn my table. I've explained how I use my values to get my conclusion. That's it. Once you do that, you get all your answers. There's another alternative way of answering this question, okay? You may choose to answer this question in terms of length, okay? So in this case now, it is the length I'm increasing and I'm keeping the mass I'm attaching constant. Yes. Don't forget that I was supposed to have said clearly that use a meter ruler, okay? Use a meter ruler to measure. So I want to put that here. Use a meter ruler to measure. Yeah. So I've answered the question again now in terms of the length, okay? So I'm increasing the length, I'm changing the mass, I'm attaching. So what will I do now? What will my table look like? My table will look like the length, okay, the length of the strip in centimeters, then initial height, initial height of the strip from ground level in centimeters, final height of the strip from ground level in centimeters, then the extension I get, extension is height 1 minus height 2 in centimeters. So that is what I can do. Okay, that's another thing I can do here. So I've explained the procedure in terms of length and extension. So those are the two ways of answering this question. The third way of answering this question is in terms of number of strips of wood that are stuck together. Number of strips of wood that are stuck together to form the composite material. Increase the number of strips of wood and then do every other thing the same way. Okay, but in that case, you'll be keeping the mass constant and the length constant. Increasing the number of strips of wood and you continue to do it, measure the E as usual, keeping the mass constant and the length constant. So those are the three ways of doing this. I deliberately did not write about the increasing number of strips of wood. So what you can do is that on your own, you can write out this procedure, okay, in terms of number of strips of wood and send your answer to me on the comment section, okay. write it as a response. Okay, write out your plan of this experiment and comment it on this video. I'll be checking your comments and I'll be responding. And if you don't want to put it on the comment section, then you can send it to my email physics.4.everybody@gmail.com. Okay, make sure you do that before the day of your exam. Okay, so at gmail.com. Make sure you do that before the day of your exam so that you can use my response to fine tune what you do and how you answer your question. Thank you for joining me today. I wish you excellent grades in your examination. Do have a nice day. See you on the next video. Ensure you subscribe to Physics for Everybody. Goodbye.